Hi. All right. We're going to continue on with carboxylic organic acids and esters into lipids. The chemistry of lipids is esters. Esters. That's why I followed lipids with carboxylic acids. Okay. Um, Now, lipids are typically very waxy unless you get down to some unique structural considerations, which are very, very small lipids, which tend to be not waxy at all. They tend to be soluble in water. Um, Typically, they are low density. That means they float. Wax floats. Um, it's a very important form of storage of energy. In other words, we burn it for energy. And it's particularly important in cellular membranes. You probably in your biology class talked about phospholipids. That's what we're going to talk about right now. Okay, these are the classifications. If we talk about lipids in general, there's saponifiable liquids. Remember, that's a lipid or a ester in an alkaline environment. And there are simple and complex ones. And then there are non-saponifiable ones. That means there's no ester. So on a test question, if I say, is this saponifiable, you look for is an ester present or not? No ester, not saponifiable. Okay, and then from there, from the saponifiable ones, we're talking about simple ones versus complex ones. The simple ones do not involve phosphorus at all, and the complex ones do involve phosphorus. Okay, so simple lipids contain a fatty acid and an alcohol. They can be a polyalcohol or a monoalcohol. Monoalcohols produce waxes. Polyalcohols produce TGs or triglycerides. Complex lipids contain other things, like phosphorus is the main one. Non-saponifiable lipids don't contain an ester. Okay, that means they cannot be hydrolyzed or taken apart. These are things like steroids, prostaglandins. Prostaglandins are important for a lot of reasons. We're going to talk about that. All right. Excuse me. All right, fatty acids. You've heard of fatty acids. There's healthy fatty acids and non-healthy fatty acids. And that varies depending on what kind of time we're in. You know, it used to be saturated fatty acids were really bad for you. Now they're not so bad for you, and etc. I guess it depends on what decade you're in. Okay, fatty acids basically are long chain fatty acid carboxylic acids. So we've got the long chain, and then we have the acid component. Depending on how long that chain is, the nonpolar chain, depends on its physical characteristics. Is it saturated? Is it unsaturated? How long is it? Lots of things like that. So they always say there's a nonpolar tail, which is this thing here. And then there's the polar head, which is this here. So fatty acids are very unique compounds because they have two parts to them. They're neither polar nor nonpolar. If we're looking at a fairly long part here, we're talking about like C10 upwards, and you put that fatty acid in water, this is what happens, is that the water that polar water is going to surround the sky. So what happens is the part that's incompatible with water, the nonpolar part, goes inward, and the polar part, which is very compatible with water, forms the outside. It's like a wagon train in the old Westerns movies. Okay, and this is 3D too. This is not two-dimensional. Okay, so uh, micelles are also called a soap bubble. Okay, biochemically in a mammalian animal, fatty acids are usually straight chained, no branching. C10 to C20, and that is totally not true. It's C4 to C20. C4 are called short chain fatty acids. They're very health-wise very important in your diet. And they're even numbered. And the reason why they're even numbered is because when biochemically we make a fatty acid in our body or in the animal that we slaughter and eat, they end up making them in pairs at a time. So they're always even. Saturated means no double bonds. Unsaturated means one or more double bonds. Cis configuration. Now, all of you have probably heard about trans fats, but you never hear about cis fats. They just say trans fats are bad, and that's true from my perspective. But they don't talk about, well, if it's not trans fat, then what is it? Well, it's a cis fat. Um, and then these are some very, very common fatty acids that you will need to know. This is, these are all C18. No double bond. One double bond. Two double bonds. Three double bonds. And they all happen in a specific place because of the way mammalians generate fatty acids. Now, the things that typically biology books fail to note when they look at a phospholipid membrane is that they always show the wrong fatty acid. They show the trans fatty acid, which is straight. Cis fatty acids are not straight at all. They're kinked. The more kinks, the more hook-like. The more hook-like they appear. So we have stearic acid, no. double bonds. Oleic is 1. Linoleic is 2. And linolenic is 3. So linolenic looks like this. Okay, this is the list of fatty acids you need to know. Not the melting points, but the structures, okay? Essential fatty acids are those needed by the body, and the body cannot synthesize those within the body. Okay, so we have, for humans, or mammalians actually in general, we have essential linoleic and linolenic. Linoleic is a omega-6 fatty acid. Linolenic is a omega-3 fatty acid. Now, I don't like the way this is produced. I like to have, okay, so you know linoleic is an omega-6. Let me just continue on and I'll show you how you can draw these easier than memorizing this. These two fatty acids, among others, are used as precursors to a lot of different things, including membranes. But there's other precursors. There's hormones, there's prostaglandins, there's all kinds of stuff. Okay, so you've heard of fats and you've heard of oils. Fats are usually from animal sources. They're solid at room temperature, except for oops, let me um, except for palm. Well, that's frequently kind of marginally solid, marginally oily at room temperature. Okay, oils are usually liquids at room temperatures, like your typical seed vegetable oils. And I specify seed versus non-seed vegetable oils. There's two kinds. A seed oil would be like canola, corn oil. A non-seed oil is going to be like, so we have seed, non-seed. Seed oils would be like soybean, canola, corn. Non-seed would be like olive or avocado. Okay. Stay away from those. These are good for you. That's supposed to be a smiley face. Okay. Typically, fats are saturated. oils are usually unsaturated. Now, the most common way that fatty acids are distributed in the body is something called a triglyceride. Okay, so we have a ester bond here. That connects the alcohol to the acid. Through an ester bond. So, and these are called frequently, when you see on your blood test, TGs. A very important metric for looking at the quality of your blood. And secondly, when you get your blood test, you will get low density lipoproteins and high density lipoproteins. Okay, the problem is high density lipoprotein metric is not as reliable as a triglyceride or TG metric. So the best way to look at it is LDL and TG. And on your blood test, it'll give you a window which is healthy, non-healthy. Now, okay, so this is what's going on here. Here is the ester right here. And because it's a triglyceride, there are 3 esters. And natural triglycerides are usually not usually, but always a mixture of different triglyceride molecules and also triglyceride acids. So these are again, the acids and the alcohol. Those don't look very good. I mean, okay, so if you remember from last Monday's lecture, we can saponify an ester to the acid salt plus the alcohol. Okay, so if we put a triglyceride in a strong base, like we did when we were making soap, like sodium hydroxide, we're going to end up with the acid salts and the alcohol. And these are called the surfactants. soap, and emulsifiers. Those are one and the same. Surfactants, soap, emulsifiers. Now, to be an emulsifier, surfactant, or soap requires a molecule with a polar part and a non-polar part. Okay, if you look at soap, we've got the non-polar part, non-polar part, non-polar part, polar part. So those are all soaps or surfactants or emulsifiers. So we can make a triglyceride by making an ester. An ester requires an alcohol and an acid. And the acids in this case are fatty acids, stearic acid, which is a C18 acid, which is a saturated, doesn't have to be saturated as long as it's an acid, but stearic acid is a C18 saturated, no double bonds. Glycerol, now it doesn't have to be a 3 alcohol or a triol to form an ester, but to form a or triglyceride, it's got to be a 3 carbon. So this is required for a triglycerol. We can also take it apart in an acidic environment. Now, you need to know this enzyme lipase. Lipase takes apart triglycerides in your small intestine. So if you mess up your lipase, you'll have trouble digesting fats. Okay, so when you, in an acidic environment or in an enzymatic environment, including lipase, and that's at pH of 7, because that's your small intestine, you produce glycerol and the acids that were used to produce the ester. Saponification, as you remember, is the same kind of reaction, only in an alkaline environment. And you end up with your acid salts and your alcohol. Okay, it depends on whether you use sodium hydroxide or potassium hydroxide for the preparation of our soap. Now, in our lab last week, we used sodium hydroxide or lye to produce our soap. That's why our soap end up being hard. If we were to use potassium hydroxide, we would end up with a liquid soap. Okay, now interestingly, historically, soap was made from usually pig fat. Pigs were slaughtered, and then they kept the lard for making soap, among other things, but mostly for making soap. So whenever the colonists were coming across our country in Calistoga wagons, etc., they always had pigs with them and stuff. And they would get the fat from the pig, and the lye they would get from taking wood ash in water. And the wood ash in water ends up being sodium hydroxide. And then they would boil it and they would get soap. Soap making was lost with the fall of the Roman Empire. So we had a soapless centuries in general. There were sporadic places where they made soap, etc. But in general, it was gone. And because of the unsanitary conditions of Western Europe, rats and fleas flourished. And the main vector for transmitting the Black Plague was fleas on rats. So you can blame lack of soap. Okay, we can take the fatty acids that are unsaturated with double bonds, and we can saturate those, if you remember from our flow chart, with some kind of a catalyst. It could be nickel, it could be platinum, it could be lots of different metals. And they would end up saturating the double bonds on the fatty acids on the fat. That would make them more lard-like, more solid-like for baking. The problem is you ended up with because this process wasn't 100%, you ended up with converting the cis double bonds to trans double bonds. So Cisco was known for that. Okay, so this is the reaction map for lipids. Now we're going to start with triglycerides. There's some other things we're going to be talking about besides simple triglycerides. Okay, so in an acidic environment, we end up with the alcohol plus the acids. In a basic environment, we end up with the acid salts plus the alcohol. In a hydrogen-rich environment with a catalyst, we end up with more, that's the key here, not 100%, but more saturated triglycerides. Okay, all of you have heard of waxes, candle wax, etc. Candle waxes are the simplest lipid. They, instead of a glycerol backbone for being the alcohol, it's a one hydroxyl group alcohol. And they're very, very long. We're talking about C30 and a long typical C18 acid. So if you you're going to end up with the acid plus alcohol in a alkaline environment, you can end up with the acid salt plus the alcohol. Okay, so there's a group called phospholipids, which are extremely important. And that's instead of 3 fatty acids in the ester, there is a phosphoric acid ester with some kind of some other attachment to the phosphoric acid. Frequently, it's an alcohol and an amine group on there. Amino, call it an amino acid, like um, choline, for example. Choline looks like this. Oops, let me do. So that's choline. So this is a phosphatidylcholine. You've probably heard of that before. So this is what we're looking at here. This is everything we studied so far. Now we throw in phosphoric acid, which is a triprotyl acid, meaning it has 3 hydrogens that can come off. Okay, so one forms an ester, and the other ester is to the amino alcohol, like choline, and there are other things. So lecithin, if you've never heard of lecithin before, it's in egg yolks. And it's a wonderful emulsifier. When you want to make mayonnaise, you want to make various cream sauces, etc., you put in an egg yolk and it emulsifies the oil and the water-based ingredients. It's also in Caesar salad dressing. It's used a lot. Cephalithins are same idea, only it's not choline. They use either this or that. So you need to know this. Lecithin. So here's the choline. So here's the phosphoric acid, here's the glycerol, and here's the choline. And this doesn't matter. It can vary. It really doesn't matter. Here's some other examples. Okay, so I'm not gonna cover these because we have a shortened deal because of my health. Now I want to talk about this a little bit more. As you know, carbohydrates have a lot of OH groups. So they can interact with various things that include a fatty acid and other things. For example, here we've got galactose. because galactoside are numbers like that. And it happens to be a beta galactoside because the OH group here is going up. It is not a reducing sugar because there's no hemiacetal. There's a full acetal here. And this is a good test question for test 2. Anyway, so we can have lots of combinations here. Now, steroids are non-saponifiable, meaning there are no esters present. This you need to know, this basic group. So all steroids will have this basic ring system. So we've got 3 C6s and a C5 in a particular configuration. So this is C6, C5. And they have to be in this order. They cannot be strung straight across. They have to be 1, 2, and then up 1, 1, 2. Okay, and there's various steroids. They're very, very common. Cholesterol, you've probably most popular one you've heard of. Now, prostaglandins are another interesting molecule. You take a omega-6 arachidonic acid, which is one of the acids you need to know, and if it's in the presence of a COX-1 or COX-2 enzyme, COX stands for cyclooxidase, it'll produce a prostaglandin. Prostaglandins are a whole host of products in the NSAID category. So NSAIDs are like aspirin, ibuprofen, naproxen, acetaminophen, and they produce these prostaglandins, and there's 2 kinds. And there's the bad kind and good kind. When you take an NSAID, you produce or you decrease production of COX-1 and COX-2. Now, the problem is COX-1 is the good prostaglandins that do things like lower blood pressure, increase anti-inflammatory activity. The bad ones are like they reduce blood clotting. That's why people say that, or doctors say that you shouldn't be taking aspirin if you're prone to ulcers because it'll prevent blood clotting. Anyway, so the bottom line in this is there are one of the reasons why it's important to take your fats in the appropriate type of fat is they're precursors to other things. Our body is full of this concept of the precursors. Okay, structures to know. Okay, we have fatty acids and general structures. These are the fatty acids. These are the general structures. And I'm going to cross out these guys. And this is lecithin. Okay, so what I'm going to cover when I get back next week is the test stuff. And then after that, I'm going to be going over reactions for Unit 3. And then we'll have a test fairly soon after that.